Okay, so the recording has started and I'll start with the lecture. So in yesterday's class, we were discussing this, the Mohs circle in 3D, and we were discussing certain things that uh, this was basically with reference to this question. So let me just go to our tutorial sheet. Where was the question? So this was the question number 10. I hope all of you can see this. This question number 10.
Yes, sir.
Yes. So these three inequalities, the left hand side and the right hand side of these inequalities, they contribute towards the equation of the circle. And as we had mentioned yesterday, the first circle corresponds to the principal stresses sigma P2 and sigma P3. So if we go back to the writing app, this is the first circle, the C1, that is associated with the sigma P2 and the sigma P3. This was our C2. If we just check, it was associated with the sigma P3 and the sigma P1. So the circle C2 is associated with sigma P3 and the sigma P1. And circle C3, it is associated with sigma P1 and sigma P2. Now, so this is our circle C3. And we had also said that when we were plotting out these things, before that, we had arranged our principal stresses without any loss of generality in this particular form, where sigma P1 is greater than sigma P2 greater than sigma P3. So without any loss of generality, we can arrange these things and then we can go about drawing these circles. Furthermore, I had also stated that because we are dealing with inequalities, the valid region given by those circles is this. So outside the circles C1 and C3 and inside the circle C2. So this is a very, very brief recap of what we were discussing yesterday. Now, this was all there is to in question number, this question number 10. But if you look at question number 11, something extra has been asked. So in question number 11, it has been asked that considering the Mohs circle for a three-dimensional state of stress as discussed in the previous problem, answer the following: what is the maximum shear stress? So because we are familiar with the Mohs circle in 2 dimensions already, we had already discussed that. Can you tell me that with respect to the circle C1, forget about everything else, just with respect to circle C1, what is the maximum shear stress? Please also note that wherever these circles, they intersect this sigma axis, because we have this arrangement of the principal stresses, this is sigma P1, this point of intersection is the sigma P2, and this point of intersection is the sigma P3. These are the principal stress values. Now you tell me with respect to the, or with reference to the circle C1, what is the maximum shear stress?
Sigma P2 minus sigma P3 by 2.
Sigma P2 minus sigma P3 by 2. Very good. So with respect to the circle C1, the tau max, and remember I have to make it a point to write this as comma in order to represent that this is the maximum in plane shear stress. So this is equal to sigma P2 minus sigma P3 divided by 2. Similarly, for the circle C2, what will be the maximum in plane shear stress? Tell me. For the circle C2, what will be the maximum in plane shear stress?
Sigma P1 minus sigma P3 by 2.
Yes. Sigma P1 minus sigma P3 by 2. And finally, for the circle C3, the maximum in-plane shear stress is going to be equal to sigma P1 minus sigma P2 divided by 2. Now, if we compare all these three circles together, so considering the overall picture, what is the maximum possible shear stress? Overall maximum. So what we call this is the absolute maximum shear stress. What is this? Compare all these three and tell me. So tau max absolute.
Tau
Which
max
one
of
of
C2.
Yes. So see, because sigma P1 is greater than sigma P2 is greater than sigma P3. So the difference between the sigma P1 and the sigma P3 is the maximum, which is why it contributes to the highest value, the highest overall value of the shear stress. So this will be sigma P1 minus sigma P3 by 2. The thing which we need to note here is that even if we are confining ourselves to viewing just the plane in which this sigma P2 and sigma P3 is occurring, it is certainly true that in that plane, the in-plane shear stress maximum value is sigma P2 minus sigma 3 by 2. But even if we are looking at that plane and someone asks us that what is the absolute maximum shear stress, then the answer will not be sigma P2 minus sigma P3 by 2. Rather, it will be this sigma P1 minus sigma P3 by 2. So for this overall state of stress in this three-dimensional case, this is the maximum possible value. Okay, so many students make this mistake. So in order to illustrate this funda, let me go back to the tutorial sheet and ask you this. So this question numbers 12 and 13, they are based on the same kind of concept. Let us consider this question number 13. Okay, so what is given for the state of stress? In fact, I can just copy paste it from here. So I don't have to keep on changing. I hope this is visible. For the state of stress, as shown in the picture, determine the maximum shearing stress when we have these three different cases of the sigma z. Now, this is just for illustration purposes, but what is the concept here? You see, for the first case, sigma z is equal to 0. Okay, but along with sigma z equal to 0, what you have to note is that on this plane, okay, so on this plane, let me just highlight it, or maybe with a different color, maybe with the orange. So on this plane, okay, on this plane, which is parallel to the xy plane, what we have, we also have the value that tau zx is equal to 0 and tau yz is equal to 0. So here we have tau zx is equal to 0. We also have tau zy equal to 0. In addition to that, we also have the sigma zz is equal to 0. Now this is a condition which reminds us that this is nothing but plane stress. Okay, whenever we have these three things to be equal to 0, we have a case of plane stress. But no matter that, what we have to actually understand is because tau zx is equal to 0 and tau zy equal to 0, what does that indicate? That the shearing stresses on this plane, they are 0. Since the shearing stresses on this plane are 0, no matter what the value of sigma zz is, in this particular case, which I'm considering for the part A, sigma z equal to 0. For part B, it is not 0. For part C, it is not 0. But as long as tau zx is equal to 0 and tau zy equal to 0, okay, these two things, they are equal to 0. What they indicate? They indicate that sigma zz is a principal stress. Because we have already studied that on those planes where the shearing stresses are 0, the normal stress happens to be the nothing but the principal stress. So sigma zz is a principal stress in all of these three cases. Part A when sigma zz equal to 0, part B when sigma zz is equal to 60 MPa, as well as part C when sigma zz is equal to minus 60 MPa. So for all of these cases, sigma zz is a principal stress. So what do we have to go about finding? So for the state of stress as given in this picture, determine the maximum shearing stress. So tell me, what should I do for this problem? First of all, what should I do? So you go from the back. Question is determine the maximum shearing stress. Okay, maximum shearing stress means our aim will be to find out the tau max absolute. If we have to find out the tau max absolute, then for each of these cases, we have to go about finding out the sigma P1, the sigma P2, and the sigma P3. Please do not get distracted by this first case where sigma z equal to 0. Even if that is so, we have to be mindful that it is actually a three-dimensional state of stress. So sigma P1, sigma P2, and sigma P3 should all be found out. So tell me, from the other components of stresses which are given, this 170 MPa, which is the sigma xx. So what is given to us is that sigma xx is equal to 170 MPa megapascals. Sigma yy is equal to 100 megapascals. What is the value of tau xy? Tell me. Tau xy, what is the value?
84.
84. And please note that in these kinds of pictures, only one of these values are given. So this 84 MPa, it corresponds to either this one or this one. They are the same. Okay, so tau yx is also equal to 84 MPa. So from these three pieces of information, can we not find out two values of the sigma p? We can find that out. Right. So all that you have to do is for the principal stresses, we have to find out for the sigma p. We have to use the formula sigma xx plus sigma yy by 2 plus minus square root of sigma xx minus sigma yy by 2 whole square plus tau xy square. If we do that, we'll be able to find out two values of sigma p, and then the other, so two values from here, okay, two values from here, and the third value is nothing but sigma zz. So once we find out those three values, we can just arrange them in decreasing order as sigma p1, sigma p2, and sigma p3, and then we can go about finding out. So I just go. After we have done that, so we have the sigma p1, sigma p2, the sigma p3 in our hand now, and from this we can find out the sigma p1 minus sigma p3 by 2, and this is going to be equal to the tau max absolute. That's it. Okay. If you do not arrange it in this decreasing order, then what you have to do is you have to find out all these different pairs, sigma p1 minus sigma p2 by 2, sigma p2 minus sigma p3 by 2, sigma p1 minus sigma p3 by 2, compare those values and find out the maximum amongst them. So it is just better that you arrange them in decreasing order and not in magnitude. Okay, so you have to respect the signs also, and then arrange them in decreasing order and then find out this value. All right, so that is all there is to it. Similarly, for your question number 12 also, you have the same concept. Okay, although it seems to be like a two-dimensional state of stress, but in reality, this is a three-dimensional picture, and you have to actually recognize the fact that on this plane, the values of the shear stresses are going to be 0. So it is actually, so if you look at this picture, the x is in this direction. So sigma xx will be one of the principal stresses. Okay, so sigma xx will be one of the principal stresses, and your plane of consideration will be the sigma, will be the one involving this yz. So this sigma yy will be 30 MPa, sigma zz will be 120 MPa, tau yz will be equal to 70 MPa. And from all of this information, you can find out the principal stresses in the plane which is parallel to the yz plane. And you also have additionally the information that sigma xx is equal to 0, which is the third principal stress. And so you can go about finding out the tau max absolute. Okay, so I hope this much is clear. Yes.
Sir, can you explain, sir, why we will not consider it as why will we consider it as a three-dimensional stress?
Every state of stress is a three-dimensional state of stress. When we say that we are considering the two-dimensional version, we are basically confining our viewpoint to the two-dimensional case. So whenever we say tau max, considering a certain plane, you have to always remember that that tau max is not the absolute tau max. That is the in-plane maximum shear stress value.
But then sigma xx in this case, it is equal to 0 then. So
yes. So similarly, sigma, the tau xy is equal to 0, tau xz is equal to 0. And because you have tau xy equal to 0, tau xz equal to 0, you will conclude that sigma xx, even if it is 0, it is a principal stress.
okay, sir.
Okay.
So what if the shearing stress components are not 0? Suppose if there is a tau xz and a tau xy.
Then you have to do a full 3D eigenvalue solution for the thing. So you have to, so this is, I'm scrolling up. So these are the kinds of problems. Okay. So these are the things. Okay, you do not have the shear stresses all 0. So whatever it is, you have to do the full three-dimensional eigenvalue problem for the solution of the principal stresses. Okay. But the reason we discuss these things is that in many practical applications, you do have certain planes on which the shear stresses are 0. We know that for a fact. And those things can actually be reduced to these kinds of typical problems.
Sir?
Yes.
I have like a general doubt regarding the transformation part. Like
Yes.
in the earlier cases that we learned, we understood that we could apply some of the other learned concept here and there. But this transformation that we are learning, like where and why do we actually apply it? Like apart from these questions and something like that.
Very good question. So see, in the previous chapters, we have found out how to find out the flexural stresses or the bending stresses. We have also found out how to obtain the shear stresses. Now, those things are confined to a certain plane and confined to certain specific points of interest. But when you are actually designing something, you cannot confine yourself to one specific point. So what I'm trying to say here is that so let us say this. You have a certain beam like this. And fine, if you take a cut section, maybe like this, you take a cut section like this, you will obtain this kind of an exposed surface. And on that surface, you can go about finding out the sigma xx. You can go about finding out the tau xy. But who is to say that on another plane, which may be obliquely cut, you may not have, or you may or may not have a stress value which is higher than this. So if you look at it from the perspective of this, so this is our x-axis, this is our y-axis, and this is our z-axis. So if you look at it from the point of view of the x-y plane, this is our beam. So instead of a cut section like this, who is to say that if we take a cut section like this, maybe on that plane, the value of the normal stresses, the value of the shear stresses that will be appearing, they may be higher in value or in magnitude compared to these values that you are calculating using just the flexural stresses and the shear stresses. So how are you going to find out these things? What is the way from going from this flexural stress formulas and the shear stress which are on these perpendicular planes to these kinds of planes? So that is where you use the transformations of stress formulas, the transformation of stress concepts.
Understood,
Okay.
sir.
Okay, in fact, you can obtain these kinds of transformations as a function of x, y, and z. So you can obtain an overall picture of the maximum possible values of the stresses and the minimum possible values of the stresses at each and every point over this beam. Of course, you cannot do such a thing by hand, you have to do it programmatically, but the basis, the foundational basis of all such things is certainly what we have been discussing in this chapter. Okay, so for the design of beams and shafts, this kind of transformation of shafts, this transformation of stresses is an absolutely foundationally important thing.
Got it, sir.
Furthermore, since you asked this question, let me highlight to you something. See, in this particular question, where did it go? So here, you have been also asked to find out, in addition to the maximum shear stress and the principal stresses, the octahedral shear stress. And yesterday, Chavi was asking me in class that what is the octahedral shear stress. So I pointed out that if you do question number 7 and 8, you will know what the octahedral shear stress formulas are. But then the question also arises, why would you do this kind of a thing? Like, one may very well ask that, is it just a mathematical curiosity that you find out these kinds of complicated algebraic formulas and you give it a certain fancy name like an octahedral normal stress and an octahedral shear stress? It is not actually that. So later on, so now you're in your 3rd semester. I think it is in your 5th semester, you will do one course called Design of Machine Elements. In that course, you will do a few very important things like theories of failure, meaning that certain bodies, or in fact all bodies, they have a propensity to fail, meaning they have a propensity or a tendency to yield plastically. So who is to what is going to give you the design basis for the information that when it is going to yield plastically? So when you go about doing those calculations, the kind of things which you compare against is the yield value, but what you compare against the yield value is quite often and very, very importantly, this octahedral shear stress. And if you see, one of the prerequisite for the Design of Machine Elements course is this Mechanics of Solids course. So it is absolutely necessary that we give you some idea about these basic things. Okay, so everything has a reason. It's not just a mathematical curiosity. Okay, I hope things are somewhat clear, and I would like to go on to the transformation of strain chapter now. So what I will do for this is to take a little bit of an utilitarian approach, meaning that because our our mid-semester examinations are very close by, this is one of my favorite chapters. In a perfect world, when we have lots of time, I would like to start from the very basics and discuss quite a few things which are certainly not there in Beer and Johnson, but those are quite important. But in order that you can actually start with the problem solving of the tutorial sheets as quickly as possible, I will I will reverse the presentation of the material slightly. So first of all, I will discuss the things in analogy with the transformation of stress chapter, so that very quickly you can start with the problem sheets. And then over the next 2 classes, Wednesday and Thursday, I will finish off the rest of the things, the fundamental theory behind it. And if time does not allow it, I will maybe take another half a class or so after the mid-semester to finish it off. But the first things that I'm going to discuss, as I said, will be a very utilitarian kind of thing, presentation of the important formula in direct analogy with what we have discussed in the transformation of stress. So stress and strain are completely separate things, but it just so happens that because of the background mathematical theory, somehow the transformation, they look exactly the same. So instead of the sigma, you have the presence of the epsilon, and that is all there is to it actually. So in terms of the algebra, there is hardly any difference. In fact, there is no difference. So I'll show you. So let us go to the next page. All right. Oh, what a ghastly color. Okay, transformation of strain. So in analogy, sorry. With the previous chapter. So what are the things that we have discussed in the previous chapter? So first of all, we presented to you, we discussed a lot of things, and then we presented to you this thing. So if we have an x dash axis, which is tilted to the x axis by an angle theta, then the sigma x dash value will look like this. I will urge all of you who are present in this class to please check with the notes which are there from our actual classes, from our actual physical classes. Okay. And we have the tau x dash y dash as minus of sigma x6 sigma yy by 2. I think this is sine 2 theta plus tau xy cos 2 theta. For the transformation of strain, all that you have to do is to just replace this sigma by the epsilon. So it becomes epsilon x dash is equal to epsilon x6 plus epsilon yy by 2 and so on and so forth. Similarly for this, epsilon x dash y dash is equal to minus of epsilon x6 minus epsilon yy by 2. That's it. So the moment you know those things, you can immediately go and start solving the first 3 problems, at least from the tutorial sheet number 5. But before that, tell me one thing, what is the sigma y dash? In the physical classes, I did not discuss this directly. What is the sigma y dash? So please note what we are talking about here is a situation like this, where you have your x-axis in this fashion, your y-axis in this fashion. You have a stress element which is present here, so that on this vertical edge, you have the presence of the sigma x6. On this horizontal edge, you have the sigma yy. Then you also have the tau xy and tau yx and so on and so forth. But when you are talking about this x dash, what we are basically doing is to consider this kind of an axis. So this is our x, this is our y, this is our x dash. Correspondingly, this is our y dash. Now, here, the corresponding stress element will look like this. So when we say what is the sigma x dash, it is basically the stress on this. This is our sigma x dash, whereas on this vertical edge we had the sigma xx. So how do you obtain the sigma x dash from the sigma xx and the sigma yy and the tau xy? It has become a cluttered mess now. So from this information, that is what it is giving us. Now, from your geometrical understanding, you tell me what should be the sigma y dash,
Theta plus 19 sigma x dash.
Yes. So if we are obtaining the sigma x dash by rotating through an angle theta, so please note that this angle is theta, then correspondingly for the sigma y dash, which is on this edge, so along this direction. So for this sigma y dash, what we are going to do is to consider an angle which is this angle. So this angle is nothing but theta plus 90 degrees. Okay, or theta plus pi by 2. So you just have to understand that this is sigma xx plus sigma yy by 2 plus sigma xx minus sigma yy by 2. So I'm following exactly this first formula, but instead of the theta, I will put as theta plus 90 degrees. Similarly, for this tau xy, sine twice theta plus 90 degrees. Now you tell me what should be this. Tell me. What is cos twice theta plus 180 degrees?
Minus cos 2 theta.
Minus cos 2 theta. Very good. And what will be sine twice theta plus 180 degree?
Sin 2 theta.
No, it is also minus. In the third quadrant, it is only the tan which is positive. So it is in the third quadrant, right? Theta plus
Yes,
90.
yes.
So theta plus 180 degrees. So it is in the third quadrant. So minus. That's it. So whatever we have here, you see, I have started by writing transformation of strain, but all that I have written is the formulas for the stresses. Because it is an analogy with this, we can quickly write down in just in the next page. I will actually write down this. So even though you feel a little bit bored, I will write this down. So epsilon xx plus epsilon yy by 2 plus epsilon xx minus epsilon yy by 2 cos 2 theta plus epsilon xy sine 2 theta. Epsilon x dash y dash is equal to epsilon xx minus epsilon yy by 2. There is a minus sign here. Sine 2 theta plus epsilon xy cos 2 theta. And finally, for the epsilon y dash, just like before, we have epsilon xx plus epsilon yy by 2 minus epsilon xx minus epsilon yy by 2 cos 2 theta minus epsilon xy sine 2 theta. That's it. Okay, you can now solve some of the first few problems. But in this transformation of string, even though we say this transformation, and these are the basically the transformation things you require, there are a couple of more things we will discuss. But before we launch into that, just tell me by analogy with the stresses now, what will be in the case of when we confine our viewpoint to a single plane, what will be the epsilon P1 and epsilon P2? Somebody? It is exactly the same as before, epsilon xx plus epsilon yy by 2. So the kind of picture that we had in our mind from the Mohr circle, where it was the sigma average plus minus r. So here also it is like the epsilon average plus minus r. So you could as well have a Mohr circle for strains. Please note that when we talk about shear strains, some of you have a tendency of thinking in terms of this gamma. Please note that this gamma is equal to twice of epsilon. But in these formulas, the things which are present are not the gammas, these are the epsilons. Okay, so please do not make this mistake. Do not write for this epsilon xy gamma xy, it will be completely wrong. Okay. So these are the things basically. Now, the extra things which I want to discuss, they are basically connecting the stresses with the strains. So in terms of material behavior, what they are. So you are already familiar with the Hooke's law. Achha, before that, I want to say something more before for this. See, when we were talking about the stresses, we talked about something called plane stress. And for plane stress, we said that sigma zz is equal to 0, sigma yz equal to 0, sigma zx equal to 0. So that was considering a plane stress kind of situation which is parallel to the xy plane. Please do not make this mistake that earlier when I had said this, let me go back. When I had said that this is a plane stress kind of situation, you may as well have a plane stress kind of situation for the x plane also. Okay, so you can have sigma xx equal to 0, tau xy equal to 0, and tau xz equal to 0. That is also a plane stress kind of situation where the plane of concern is the yz plane. Okay, so you just have to have the three stress components equal to 0 for a certain plane. Otherwise, for the other stress components, they are not 0, that is fine. Now, in a similar fashion, what do you think will be the plane strain condition? Please do not take these things lightly, because time and again I have seen many of your seniors making very fundamental mistakes in this. So tell me, for plane strain, what should be the thing? It is actually epsilon zz equal to 0, epsilon zy equal to 0, epsilon zx equal to 0. Equivalently, you can have epsilon xx equal to 0, epsilon xy equal to 0, epsilon xz equal to 0, similarly for the strains involving the y directions. But as long as you have these kinds of three sets, three strain components equal to 0, you can say that this is a condition of plane strain. What is the implication for this in terms of the relationships that we have between the stresses and the strains? So considering the generalized Hooke's law, what is the relationship between the stresses and the strains in the special case when you have plane stress and in the special case when you have plane strain? Okay, so these are the kinds of questions which are actually there in your tutorial sheet. So let me open this tutorial sheet number 5. You'll see for yourself. So this first few equations, at least the first two questions that are there, maybe not the first question. The second question and a few other questions, you can directly use our strain transformation formulas. But what I want to focus right now is on these kinds of things, on these two questions, question numbers 5 and 6. So you read the question here. For the case of plane stress, show that the following can be obtained from the generalized Hooke's law. Okay, so plane stress, we have sigma zz equal to 0, sigma tau zy equal to 0, tau z x equal to 0. Now in this situation, what does the generalized Hooke's law reduce to? We all know that the generalized Hooke's law is this. So I'm going to write down the normal strings first. Plane stress. Okay, I am not considering plane strain. For plane stress, you see sigma zz is equal to 0. So this is gone, this is gone, this is gone. What does this reduce to then? Well, you don't even have to consider this third equation. See what is the question asking us. In fact, I can just, sorry. What is happening? Wait, I know what is happening. So this is our question, and okay, now you see, we basically need to find out the expressions of this sigma xx and this sigma yy. Note that there is no involvement of the epsilon zz. That is like a standalone equation. It gives us some information, but what has been asked is actually to find out the sigma xx and the sigma yy. So if you look at these three things, equation 1 and equation 2, you can actually obtain the sigma xx and the sigma yy in terms of the epsilon xx and epsilon yy. So I will write this here. So solve 1 and 2 to obtain sigma xx and sigma yy in terms of epsilon xx and epsilon yy. That's it. But you can equivalently have another question which is not asked here, but I can ask that in the case of plane strain, what happens? In the case of plane strain, what is the situation? Well, let's write this again. Okay, for plane strain, we know that epsilon zz is equal to 0. If that is so, then what this equation is giving us is that sigma zz is equal to nu times sigma xx plus sigma yy. Now, what you have to do is we have to substitute this expression of sigma zz here and here. Okay, so you substitute sigma zz expression in terms of the sigma xx and sigma yy here and here, and then you solve for sigma xx and sigma yy in terms of, again, so same strategy as before, in terms of epsilon xx and epsilon yy. So please tell me, so whatever I have discussed till now, is it okay, or do you have any confusion or any kind of special cases that you are thinking for which this kind of strategy may be problematic?
Sir, is this the case of plane strain, right? For plane
This is
stress,
this, yeah. So what I just discussed, this part. Okay, let me put a mark here. Okay. So this diagram, it corresponds to this. If you are confused, I will take it somewhere else. Otherwise, who knows, people revising later what they will think. This is plane strain, okay, completely separate. Okay, this is not even asked in the tutorial sheet, I'm just saying. Okay, I'm just discussing this. Okay, any other question regarding this? If not, let us go to the next question. This question number 6. So basically, let us consider this question number 6a. If you understand what to do with 6a, you can do 6c, and basically for parts b and d, you just sit and think. Okay, there's not much to it, but let's think about this question number 6a. What is it actually asking us? So for a material that behaves according to the generalized Hooke's law, considering the case of plane stress in the xy plane, derive the strain transformation equations from the stress transformation equations. Now the thing is, we know the stress transformation equations. We also know the strain transformation equations independently. We also know that they are exactly the same, except that the symbol sigma is replaced by the symbol epsilon. But what asked here, the information equations from the stress transformation equations. Okay, so this is just a like a theorem kind of thing. So what do we do here? Again, let us go to a new page. So we have the stress transformation equations like this, again repeating the same thing. Right. Now you tell me, what do I do? So
sir, we can write the stresses in terms of strains using
just
generalized
give
Hooke's
me
law.
just give me a second. So I am doing this question. Yes, tell me.
Sir, maybe
Somebody
we can
was
write the
suggesting something.
stresses
Yeah, we can write the stressors.
in terms of strains using generalized Hooke's law.
Right, we can do that, but which expressions of the sigma xx, sigma yy, and the tau xy are you going to use? So the
Sir,
expressions, yeah, let me say this. So see, we have to understand very importantly that specifically we have been asked to deal with the case of plane stress, and in the previous question, not this one, okay, this one I just discussed myself. In this thing, you see these expressions of sigma xx and sigma yy we have already found out. We are going to use this. Okay, we are going to use this, not the general expressions that we obtain from the generalized Hooke's law. So these also have been obtained from the generalized Hooke's law, but under the condition of plane stress. So since in question number 6 we are again asked to deal with the plane stress, we are going to utilize this. So you substitute the sigma xx is equal to E by 1 minus nu square. What was it? I keep forgetting. Right. Epsilon xx plus nu epsilon yy. And sigma yy is equal to E by 1 minus nu square epsilon yy plus nu epsilon xx. These two things are fine, but what about the tau xy? What do we do with this? See, for the plane stress case, we did not find anything special with regards to the shear stresses. So tau xy, in the case of the generalized Hooke's law, it is twice g epsilon xy. In this case also, you keep it like this. There is nothing special going on with this shear stress, shear strain relation in the case of the plane strain. What is it? What it is in the case of the generalized Hooke's law, it remains so in the case of the plane stress case also. So if you substitute these things here, you are going to end up with something. Okay, I'm not going to say that. So you do this. Okay, you do this, solve for it. So similarly, you also note that you will have the corresponding expressions for the sigma y dash y dash. Okay, so do everything. So on the right hand side, you make these kinds of substitutions. On the left hand side also, you make these substitutions and see what happens. Okay. You will be able to get it. I mean, it's not such a big deal. I mean, within maybe 5-6 lines of algebra, you can obtain the exact same. You'll get back this same form for the epsilon x dash x dash. Okay. Any question about this? Please think for a few seconds and ask me if you have any doubts. What I said, if it was not understandable to you, please let me know.
So there is a shear modulus term in the tau xy. So what to do for that one?
This twice g, right? This shear modulus. So just use the thing. So g is equal to e by 2 into 1 plus nu. This you already know from your first year.
Yes.
So then everything gets expressed in terms of the Young's modulus and the Poisson's ratio. Anything else? So if so, I will suggest that first you do this and then you attempt question number 6C also, which is dealing with the plane strain. And when you do that, what I just discussed in the previous page, okay, this one, whatever you find out with regards to this, it will be useful. Okay. So please do this. It will be very, very good exercise. I mean, not just in a pedantic fashion, but also for your exam. All right, so if there are no more questions, I will end the discussion regarding the transformation of strain here. We'll continue, of course, with the strain chapter tomorrow, Wednesday, as well as on Thursday, where I will discuss all the proper theoretical details, the underground theory. And after we do that, you'll also be able to do things like question number 1. Now, all this is fine. We are back on track with regards to, we had fallen a little bit behind because of the holiday last week, but now we are back on track. Now, some students had asked me that they were facing some problems with the shear flow questions. Basically, all those nails, horizontally stuck nails and the vertically struck nails. So I think it is a good opportunity for us to have something like an office hour where I discuss those problems and clarify your doubts, because I think quite a few of you have these doubts regarding those questions. So let us have that discussion. Let me take a 2-3 minutes break. I'll just come from the restroom and then we'll continue. Okay. So I think we can start this discussion regarding the shear stresses. So you guys please ask me. I have something in mind that I want to discuss, but let me just get an overview of the kind of things you want to have discussed.
So for the shear flow problems, the cue which we have to take, I was getting confused on the cue that we have to consider in
Very
case
good.
of.
I do want to discuss that. What else? I think this is the main issue which most of you are facing regarding the calculation of the Q. I mean, sometimes even if you are getting the correct answer, you are not sure why you are getting the correct answer.
Yes, sir.
Okay.
Yes, sir.
Yes.
All right. So let us discuss this. Let us go to the tutorial sheet. So I think if we discuss one or two problems and like really understand what is going on, then I think it will be clear. So let us take which one? Maybe this 7 and 8. Let us take. OK, I have also tried this out myself with putting the proper values and everything. So I can discuss. It's fresh in my mind also. So let me discuss first question number 8, which is slightly more straightforward. OK, tell me. You guys tell me first of all. I hope you can all see this. Question number 8. You tell me what did you do? Let me focus on this by taking it from here to the writing app. So this is tutorial sheet number 3, question 8. OK, tell me what did you do? So the question is the beam is subjected to a shear of V equal to 2 kilonewton. No confusion there. Determine the average shear stress developed in each nail if the nails are spaced 75 millimeters apart on each side of the beam. Each nail has a diameter of 4 millimeters. All right. So basically, what do you have to find out here? The force which is being sustained by each of the nails. If we can find out that force, we just have to divide by pi d square by 4, where d is the diameter given, diameter of the nails. That's it, right? Is it not? We have to find out the force which is being sustained by the nails. Now, question is, in this cross section, what kind of a cutting plane we have to consider, and correspondingly, what kind of a Q we have to consider, right? So you tell me, what did you guys do for this problem? So I think quite a few of you had asked me about this problem and the other question number 7 also, and I had suggested that you consider a cutting plane which is like along the interface over which the nails is being used to join. So how do I express myself here? Maybe through this red color thing. So this is the interface, right? This is that interface. Okay, this is that interface. So my suggestion was that you take a cutting plane along that and then you consider the Q. And some of you were saying that, OK, sir, you were saying like that, but that means that we take, suppose I remove all of this. That means I just take this vertical board here, but some of my friends are getting answers if they take this middle board. And some of you have also seen the solution manual of this, which you are not supposed to see, but OK, I understand. You have seen the solution manual and probably there it is given like this. This board is taken as for the Q, right? These are the various confusions. Is it not?
Yes, sir.
Okay. So who has done by taking like this middle board? Let me see.
Sir, I have done like that.
Who is I here? Parijat.
The
Okay. Okay. Anyone has tried by taking the legs, those vertical boards? No?
Yes, sir. I have tried with the legs.
It is coming.
Yes.
Answer is coming. Okay. Now confusion is why are you getting the correct answer? That is the doubt. All right, let's see. So see, first of all, the most natural thing for us to think, like this is a physical problem, the nails are joining these two boards, this horizontal board and this vertical board over this vertical plane. So there is nothing wrong for us to think that, okay, we have to consider this vertical kind of a cutting plane. And there is nothing wrong for us to think that why not take this Q itself? Q for this vertical board itself. What is so bad about it? And you may also think that, okay, so then why am I getting this thing, this for this horizontal board? Now, before we can discuss any of these things, you please try to understand one thing. This I had mentioned earlier. We have this rectangular cross section, right? And very easy, this is the neutral axis. Fine, this is our y. This is our y axis, this is our z axis. X is coming out of the plane. Now, suppose I say that across this interface, okay, across this interface, I want to find out the shear stress. Then the natural choice for you would be to take this hatched part, okay, this hatched part, find the Q for that. If you know the thickness of this, okay, maybe the thickness is something like, I don't know, maybe something like H1, and maybe this entire height is H. You can go about finding the Q for that. And I had already mentioned this to a few of you that fine, you can find the Q for this. So this one will have a certain Q value. But equivalently, you can find out the Q for the bottom part also, for the rest of the cross section. What do you think will be the relationship between Q and Q dash?
Q plus Q dash equal to 0.
Q plus Q dash will be equal to 0. Very good. Okay, so basically Q dash will be equal to minus of Q. That is it. This is something which you have to fundamentally understand. Okay, now let us go back to the problem. Here, some of you are getting the answer by considering this vertical board. Some of you are getting the correct answer by getting this horizontal board. Now, is it not true that when you are considering the vertical board, perhaps you consider both these vertical boards together? Okay, I know some of you want to jump at this statement, but just for argument's sake, just hold on and see. You consider this vertical board and that vertical board together. Then this horizontal board is just the rest of the cross section with respect to those vertical boards. So if this is the entire cross section and you consider these vertical boards, then the horizontal board is the rest of the cross section, is it not? Then it must be true that if the Q corresponding to this one and this one is like Q, then for the horizontal board it must be minus Q. Okay, by our previous, just the funda that we had discussed in the previous page, that must be true. Agreed or not? Tell me something.
Yes, yes.
Agreed. Okay, agreed. That has to be always true. So if you take an entire cross section and you take out a part of it, the rest of the part must have the minus of the Q. But there is a little bit of a subtlety here. So you see, noticed how I have taken both the boards, right? I've taken both the boards. Why did I take both the boards? What did I actually do by taking both the boards? If you can understand
There are
this,
two
that
rows
means you
of
have...
nails here.
No. Even if let's okay, very good point. Very good. You said that. So our picture. So if I just look at the cross section, it is like this, right? This is our one board. This is another board. It is much easier to draw on a board, on a chalkboard, instead of this writing app. So this is, what a horrible picture. Okay, so this is our picture, but as opposed to this, suppose I take a picture like this, where instead of two boards, I have another thing like this. Suppose I have an L-shaped board. Okay, this is my L-shaped board. This is one single board. There are no nails or nothing. Okay, just from a piece of log, I have cut out this L section, this continuous thing, and that using nails here, I have joined with this vertical board. Okay. Now, you tell me. Whoever was saying that because of the nails, I am considering both the boards.
So this is basically similar to the case if we take one of the vertical slabs.
No. My question is not that. Listen to my question. My question is, in this case, what do I do for the Q? Can I say that if I take this Q for this, the rest of it is going to be same, minus of that?
No, sir. We took the axis perpendicular in this case compared to the last example.
Axis perpendicular to what?
I mean, in the last example, the horizontal line was taken for q plus q dash equal to 0. Here it is the vertical line.
You mean the neutral axis?
Yes.
So the cutting plane is perpendicular to the neutral axis. That is what you are worried about?
Yes, sir. So how can we write in that case q plus q dash equal to 0?
No, alright. So come back to this picture, okay? What I'm saying is, you take the Q for this, okay, together with this. Okay? About this axis, about this neutral axis. Okay, about this axis itself. This Z axis. Okay. So I'll write this very clearly. Q about the Z axis. Fine.
Yes.
Is it going to be, so these two together, okay, these two together is this QZ. And this is, what I'm saying is this is going to be minus QZ.
Understood. Got it.
This you have a little bit of, this you had a little bit of a problem digesting, right?
Yes, sir. Now understood.
Why have you understood?
Despite whatever the neutral axis is, there would be some part that is below the neutral axis which would give a negative component. No matter how we have taken the cutouts or the consideration, like whatever section that we have taken. So it will eventually lead to 0.
Right. What about this thing? What do I do here? So for the calculation of the Q, I am taking the cutting plane at that place where the nails are joining, right? But there are no nails here. So should I be taking like a Q here also?
No.
But actually, you see, if I have to, you can check this, okay? What I'm saying, you take this and you take this together. You can take an imaginary cut through this. There is no problem. Imagination is imagination, right? You take an imaginary cut through this. Again, consider the QZ for this, considering these two. whatever will be left here, now this thing, this will be still, sorry, this will be still minus QZ. Now what happens that if you do not take this thing, this you check yourself. Okay, I'm not going to say anything. You check yourself. Suppose you say that only this part is the QZ. Okay, suppose this part is the QZ and whatever is not hatched, here, only this right hand side leg is hatched. Okay, this is the QZ. Will it be true that for this L-shaped log, will it be minus QZ? Think about it. I hope you have understood my question, right? So these two legs taken together, it is contributing a QZ, and this board will be giving us a minus QZ. But suppose I take only one leg, take that as QZ, can I claim that this other part will be minus QZ? Because as far as the complementary part of the whole cross section is concerned, this is holding true. This is my entire cross section, one part I have taken, I'm saying that that is QZ. Then the rest of it must be minus QZ. Is that going to be true? Or if you have any doubt regarding this, what is the fundamental question which I'm implicitly asking you here?
The position of the neutral axis is not changing, so YZ, YC into total area is equal to 0. So it should be minus QZ for the remaining part also.
Okay, you try that. Okay, take this kind of a simple cross section and try to find out the QZ. Okay, for this you find out the QZ. For the rest of this horizontal plus this vertical leg you find out. Okay, see if it is actually equal to minus QZ. I think if that portion you clarify for yourself, everything will be clear. But I will not stop. Okay, I will leave this as a homework. Okay, check whether this is actually equal to minus QZ. You do that on your own time. But let us try to solve this problem actually. Okay, so
I guess it wouldn't be equal to minus QZ.
check.
Not like we can even think about it like the Q of the right leg would be equal to the left leg.
Yes.
And the upper part would be some addition or subtraction to the one leg.
Yes,
so
yes,
it shouldn't be equal to.
You're right. You're right. But see, that is like a JEE mains kind of elimination procedure you have used. But fundamentally, what is the problem here? Why it is not matching like this? Because see, when you are doing this Q, you are basically taking the first moment of area about the neutral axis. Right, you're taking the first moment of area. You're basically doing an integration of YdA. Is it not?
Yes.
So when you are doing that integration of YdA, the moment you break the symmetry about the vertical axis, it creates a problem. You think about it.
Understood.
Okay. But let us try to solve this problem. So what I like to do for these problems is I will not take this 225, all these things. Okay, it creates a lot of confusion. If you look at the solution, some of you have already looked at the solution manuals. All of those things are solved in terms of these numbers, and it creates a confusion what is going on where. So I think it is better to solve in terms of variables. So what I'll say is this B is equal to 200 millimeter. Okay, the width of these vertical boards, I will call them as the thickness of the webs. So TW. So TW is 25 mm. And the thickness of the board, that I will call like a flange. Although these are not properly flanges, but just bear with me. So thickness of the flange will be, how much is the thickness? 50 mm. Okay, Then what else we have? Height. Height is there is only one height, that is also 200 mm. Anything, any other dimension that I have missed? I think I have covered everything. The distance between the these things are given 75 mm. Now, what I want to do is I will take, let's say for argument's sake, I will take this this part, this board. Okay, so what I'm basically doing is this. Okay, and I take this part. Let us find out first of all the y bar. I believe all of you can find out the y bar, but I'll show you the calculations that I have done. Okay, so this y bar all of you can find out. I'm not going to write all of these things. And after you find out the y bar, you can also find out the I. Okay. Now, suppose I proceed just with this vertical part for the Q. Okay, so just bear with me. If I just find out the Q, then what do I need to do? I can find out the Q, no problem. I mean, I know the y bar, the location of the centroid, I can find out the Q. It's just a rectangle. What's the big deal here? So I mean, just to write it, what is the thickness of this web? So it will be TW into the H, that is the area, and the distance from the this thing will be something like this y bar minus H by 2. Okay, if I calculate the position of the y bar from the bottom location, from the bottom edge, so it will be like this. Okay, no problem. And then what do I do? That is the crucial step. Tell me. For the calculation of the everything to do with the nails. So force in the nails,
Force
right?
per unit, force per unit length.
Force per unit length. Force per unit length will be this F by S. Fine. This should be equal to what? So force per unit length is like the shear flow. So this will be equal to VQ by I. Right? Is it not? You tell me, should it be twice F by S? Because there are two sets of nails, na? Should be twice F by S.
Considering only one of the boards here.
We are considering only one of the boards. Okay, this is very important. We are considering only one of the boards. If for the calculation of the Q, you consider both the boards, then it will be twice F by S. Fine. Furthermore, and listen to this part very, very carefully. Now we are considering only one board. The way that you go about doing this, please do not directly compare this through another alternative method of solving this problem. Maybe some of your friends have done this, where they are taking this horizontal board. Because if you take the horizontal board, in fact, I'll write this. If you take the horizontal board, if you take the horizontal board for your Q, then what will be the corresponding formula for this? Tell me. See, in that case, there are nails on this side, there are nails on this side also. Is it not? Because in order to isolate this board, you have in fact taken two cutting planes. So it will be actually twice F by S. That will be equal to the V Q by I. Okay, let's call this as Q1 and this let's call this as Q2. Right, but please note that this Q2, what is the relation between Q2 and Q1? If you can answer this, then all your doubts will be
Q2
clear.
plus 2Q1 equals to 0.
So 2Q1 plus Q2 is 0.
Q2 plus 2Q1 will be equal to 0. Very good. And please don't worry about the signs, okay? The signs are going to be opposite does not mean that it has only to do with the fact that how you are considering the direction of the shear stresses. Okay, that is the only thing it is indicating, because they are on complementary planes. Okay, so on or rather opposite planes, that's why it is like that. But other than that, it is not giving any other information, that minus sign. So Q2 in magnitude will be twice of the Q1, and it makes sense because in the previous method of doing it, we were taking this one board, but had we taken both the boards, then we would have twice Q1. Right, and when you took twice Q1, then on the left hand side of this equation, what should be the force? It should be actually twice F, because then we would have to consider both the nails. Is it not? So see, if we take twice F here and twice Q here, twice Q1 here, it becomes exactly equivalent to this picture, to this way of looking at it. Is it not?
Yes, sir.
So I hope this gives some clarity to the overall picture. Okay, so let me show you the calculation for this. This is question 8, no? So I have done the Y bar and all these things. So I just want to show that I am getting the perfect answer also. Okay, now if you want, I can share this files. You can play around with it, or you can make it yourself. For the Q1, you notice what I have done. For the Q1, I have taken this thing. What to say? That horizontal board. Okay, can you see this actually? Okay. For the Q1, I have taken the horizontal board. And for this, I have taken both the vertical boards. It is both the vertical boards because here is a multiplication by 2. So this you see here, this multiplication by 2, that is why. Okay, so that's how I go about doing it. And this 2 factor comes because it was actually twice F that I had considered. All right. So if you don't have the 2 here, you won't even have the 2 here. It is still going to give you the same answer. Okay, so you can check all of these things yourself. Okay, next, let us take the slightly more involved example. This question number 7.
Excuse me, sir.
Yes, tell me.
Sir, so if the pin was only in the one side, then the 2 factor wouldn't come, right?
If the nails were only on one side.
Yeah.
Yes, then the 2 factor would not be there.
So we would
So
be
the
taking
answer would be
Q1
same.
only.
No, see, in that case, the horizontal board also would not have the 2 factor. Is it not? Whichever way you do, for the horizontal board also there will be nails only on one side. And when you do the vertical board, then also nails on one side. So 2 factor will not be there. It will match. It will still match.
So only Q1 we would take in that case for Q.
Sorry?
So if there were nails on only one of the sides, so
Yes.
we would be considering only Q1 as our Q.
Like I have taken here, right?
This.
Yes. Yes. Absolutely.
Sir, but then even then we could have taken Q of the middle board to be equal to 2 times the Q of the side boards.
Sorry.
Sir, let's say there was no nail on the right side,
There
and
was
then
no,
we had
there was no nail on the left side. Let's say like that.
left side. Okay.
Okay.
Sir, then from the approach of taking the left board, the same equation would be same f by s equals to 2 bq1 by I. But even then, Q2 would be equals to minus 2Q1. So,
Yes. Yes. And then
but
you
in
are
the
saying
middle
that,
board, we wouldn't have taken.
then you are saying that if we take just F here, then the shear force
Yes,
will not match.
yes, sir.
Yes, you are right. Because you see, in that case, and you will actually see this kind of a discussion in certain books, that in that case, what is actually happening, that you have isolated this board out. On the right hand side, the support is being provided by the nails. But it is not that as if from the left hand side there is no support. Who is providing the support from the left hand side?
The material itself.
This, the actual wooden material is providing the support. So there is actually, in order to keep this thing like this intact, there is actually a shear force which is very much equal in magnitude to the shear force which is being supported by the nails. Actually, it is the other way around. If the material had been one piece, then the wooden material itself would have provided the required shear force. But there is no fiber which is actually connecting the wooden fibers which are connecting this. The absence of those wooden fibers, the natural fibers which would be supporting it, that responsibility is being taken up by the nails. Right, that is why this F is coming for the nails. But if we isolate our board like this, then still you'd definitely have to account for the fact that there would be a shear force here. But that shear force is not by the nails, it is by the wooden board. But the F will be F. So that will still be the twice F.
Okay, sir.
Okay. I don't know if this particular thing is discussed in Beer and Johnson, but it is certainly discussed in Hibeler. Okay, in R.C. Hibeler's book, this thing is particularly absolutely discussed. And I think in one of the solved examples or somewhere it is discussed. Okay.
Sir,
Next.
what is the general rule for choosing the Q for these type of problems?
There is no general rule specific to, considering specific problems, you find out the Q by the method which will involve the least amount of work for you. Could you hear me?
Yes, sir. Yes.
Okay. Okay, next problem, this question number 7. Okay, so the beam is made from 4 boards nailed together as shown. If the nails can each support a shear force of 500 Newton, determine the required spacing S and S dash if the beam is subjected to a shear force of V equal to 3.5 kilonewton. Okay, so this gives us an opportunity of looking at this problem from various different points of view. So let's do this. So first of all, let us take the S, these horizontal nails. Okay, so across this vertical plane. So see, I'm not going to discuss the centroid and the eye. Okay, you can find that out. But let us discuss the Q. So you tell me what to do with the Q. Give me suggestions. Suppose I say naively, okay, suppose I say that for the Q, I will only consider this bit, okay, this thing, just this bit. Okay, this portion. Will it work out? Can I just consider that Q? Think about it. Say yes or no something. I mean, I'm not in a physical class. I cannot see your faces. I don't even know connection is there or not.
Sir, I had taken the middle board, sir, because there are nails there also in the middle.
Okay, we'll come to the middle thing. We'll come to the middle thing. But my question is, can we take this this little piece?
Yes, sir.
I think we can, right? If we take this little piece, so again, I will consider this thing like this. This is the web. Okay, this is a proper web. So TW, that is how much? 40 millimeter. The height of this web is how much is it? 250. What is the width of that flange? Width is 250. The thickness of the flange, how much is it? 25 mm. Okay, now for this little bits, I will call that height as HT. HT is how much? Tell me. Height of those bits. It is 50 mm plus 25 mm, 75 mm. And the thickness of those bits, TT, it is how much? 25 mm. Okay. Now suppose if I consider just this bit, little bit, then for that Q will be how much? Tell me. Suppose for the calculation of the Y bar, I have started from the top edge, because most of the things are near the top edge. All these complicated little joinings are near the top edge. Suppose my reference is that top edge. Okay, so Y bar calculated with reference to the top edge. Then for the Q corresponding to that little bit, how much? Thickness is TT, height is HT.
Multiplied by y bar minus ht by 2.
So HT into TT multiplied by Y bar minus HT by 2. Right? Everyone agreed with this?
Yes.
Yes, sir.
Okay. Now, from the previous discussions, you tell me. Somebody just now said that he has done this problem by considering the horizontal board. Okay, this horizontal board. Is your answer matching?
Sir, I think it matched. As far as I can remember.
It
Or
matched.
maybe there was a small error.
Okay, let me discuss it properly. You see, we have taken the Q for the small bit like this. Now, very naively, we can think that the rest of the cross section is the complementary part, but we'll be a little bit wrong there. The same mistake that we would be committing as in this problem. Okay, if we just took this Q and said that the rest of it would be minus of Q, that would be wrong. We have already seen that. So here also, what you have to actually do, we have to take this bit together with this bit. Okay, it just means that this gets multiplied by 2. So what we are in fact doing is we are considering both these things. We can do like that. Okay. If we do like that, then the forces associated with the nails will be twice of this twice f. Right? Why are we doing all of these things? What is the big advantage of taking this twice f? Is there any particular advantage, or could you have just, without taking this without taking this this 2, can we proceed? What do you think? Can you proceed without taking the 2? Suppose I say that I will take only one series of nils. I will just take f. I will not take twice f. Let's see what happens. Okay, let's see. Suppose I don't take this. I'll come back to this consideration. Okay, taking both the bits. So if I have this, then my f by s should be equal to, again, vq by I. V is given to me. Q I have already I have just now calculated. I also I know how to calculate f by s. So F is given as 500 Newton. I just have to find out the S. Suppose I take both these bits, then it will be becoming just multiplied by 2. Correspondingly, this will become twice of F. So there is no particular advantage if I consider just these 2 bits. Okay. In terms of my calculation, I'm just involving another factor 2 on both the left hand side and the right hand side. But in terms of the overall understanding, suppose I take 2 bits. Okay, suppose I take 2 bits, then the complementary part of that will be what? Of this cross section? Is it just the horizontal board, or is it the horizontal board plus this vertical board? I'm repeating my question.
Plus rest of.
So I'm repeating my question. If I take this bit as well as this bit, then for this entire cross section, the complementary to both these bits is not just this horizontal bar, or not just this horizontal board. It is the horizontal board plus this vertical board. So if you take a Q, let's say this is Q1, let's say Q2 is just the twice of Q1 when you're taking both the things. Then if you have to match with this Q2, it is going to be both this horizontal board and this vertical board. Okay. That will be the complementary part of this cross section. If you just take one single board, then you can't take this horizontal board plus this vertical board plus this vertical little bit to say that the Q of that whole thing is going to be the minus of this. That is going to be wrong. Okay, the same kind of mistake which we were doing earlier with the table-like structure. Okay, so you have to consider both these bits, and then only you can say that whatever the remaining piece is, that will be the minus of, that will be having the minus of Q of this. And again, the argument is that you are basically considering parts which are vertically symmetric. But if you don't want to go into all of these complications, just proceeding with this Q1 thing where you are considering only one bit, just considering one row of nails, this is perfectly fine. Proceed like this. There is no problem. Okay. Is it okay?
Yes, sir.
Okay. Next, for the S dash. I'm just repeating this thing here. For the S dash.
Excuse me, sir.
Yes.
Sir, can you explain once again if it will be if the Q of both the small slabs taken together will be equal to the rest of the part?
What do you need me to explain?
I did not hear what you said before that, so that's why.
Here.
Yes, sir.
So what I'm saying is, if you take the Q of both these little bits, That will be what? Twice of this thing?
Yes, sir.
Okay. The counterpart of that, I mean the minus of Q2 will be contributed by what? It is not just the horizontal part. It is the horizontal part plus the vertical part.
Yes, sir.
That is what I said.
Okay, sir.
Okay, but on the other hand, if you just take the Q1 contributed by this one bit, then you cannot claim that this horizontal part plus this vertical part plus this little bit is going to contribute a minus Q1. That will be wrong. Because then
Yes,
you
sir.
are violating the symmetry about the vertical axis. Okay, that is what I said. Okay, let's come to this for the S dash. So this S dash, they are corresponding to the, it is corresponding to the vertical nails. So we have to take a cutting plane which is perpendicular to this vertical nails, means a horizontal plane. Okay. So when we take this horizontal plane, let's say this is our horizontal plane going through like this. Okay, we are just slicing through this part where this A is written between the at the interface between the horizontal board and the vertical board. We are making this pink colored cutting plane pass through that. Okay, I'll just remove this plane. Now you tell me what will be the easiest way to proceed with the Q? See, Y bar, I, all of this, all of those things are the same. For the Q, what will it be?
The middle board.
Middle board, that vertical board, because that is just one rectangle. Okay, so Q will be what? Tell me. So I'll just copy paste the things from here. Okay, now you tell me what is the Q for that vertical board? H must be there. Thickness of the web, that should be there. What will be multiplied with? What will be the distance of this centroid from the top edge?
H plus HT minus Y bar.
H plus TF actually. Thickness of the flange is this much. Okay, that is the flange thickness. So it is TF plus H by 2. Okay, TF plus H by 2 minus of Y bar or Y bar minus of this entire thing. I like to write it the other way. So it is Y bar minus of this. This will give you the Q. Now, this is simply F by S dash. This is equal to this Q is this Q divided by I. This will give you your S dash. Okay, this will give you your S dash.
So why is it not the board in middle?
This is the board in the middle.
No,
I'm
no, I
considering
mean
this.
no, not that one, the horizontal board.
Horizontal board you want to consider. That's what I'm going to discuss now. Okay. So we are considering the vertical, this horizontal cutting plane now. What we have just now considered is the part of the cross section which is below the cutting plane. Okay, but as you correctly pointed out, why not take the part which is above the cutting plane? But please note, above the cutting plane, so above that cutting plane, what is the rest of the cross section? Is it just this horizontal board or is it the horizontal board plus these two small bits?
The two small bits also.
Yes, that is the thing. So we can actually do alternatively. It will involve a little bit more calculation, but theoretically there is no problem. So for the Q, what will it be? Tell me. What will be the contribution from the horizontal board, that part? Thickness is TF and the width is B. So B into TF. Okay, then y bar minus TF by 2. That is the contribution from the horizontal board, right? What will be the contribution from the vertical, these small bits? I'll first put a 2 overall. Then HT into TT, right? Then y bar minus TT by 2. Okay. Please check if this is okay or not. So let's say this is Q1, this is Q2. You should check that Q2 is actually going to be equal to minus of Q1. Okay, this must be true. Q2 must be equal to minus of Q1.
Excuse me,
And then
sir.
also your this thing. So this is your Q1. In terms of the calculation of the S dash, it is exactly the same thing. Of course, with the, I mean, you have to consider their magnitudes, okay? Otherwise, sign will be a problem. Yeah, tell me.
Sir, why did we take in the calculation of Q1? Why did we take TF plus H by 2 and not just H by 2?
Because the y bar, it is calculated with respect to the top edge.
Okay, okay.
Okay. So within the y bar, there is a contribution from the TF.
Yes.
All right. So let me just demonstrate to you that this actually is, what happens. So. So this is the same problem. You see, just slightly reduce the font. So see, first I've calculated the y bar and the I normal way with respect to the top edge. And then this Q1 I have found out like this. So this is for the S. I want to show for the S dash. For the S dash is this one. So okay, for S dash. So see, for the Q1, I have done exactly like I've actually, let me take this to, you can see side by side then. I hope you can see this. So see, for Q1, H into TW, H into TW into Y bar minus TF plus H by 2. So I have done the this thing. I have done the S dash 1. So this value, the second last value that you are seeing with the minus sign, I have not adjusted for that. That is this 30.7 millimeter, which is, I believe, the correct answer here. Yeah, 30.7 millimeter. And if I take the Q2, like I have done here, by taking all of these things, this B into TF into Y bar minus TF by 2, all of these things, I've written it exactly like I've written here. Okay, so you still get the same value, same magnitude, okay, 30.7 millimeters. So I hope this is a little bit satisfactory to you now.
Yes.
Sir, can you please once again explain the why did we do the two bids for S dash?
Why did we take the?
Like the two corner blocks for the S dash.
Right. So see, our cross section is like this. Our cross section is like this. Okay. When I'm doing it like the Q1, I'm taking this part, the Q1 corresponding to that. When I take the other case,
Yes.
then I have to take whatever is left of the cross section. My cutting plane is here. Okay, my cutting plane is here. My cutting plane is here. Sorry. So whatever is below the cutting plane is this. For the ease of my calculations, I've taken the Q1 here. But if I take, just for concept clarification, if I take the part of the cross section above it, it is not literally above it. It is actually what is on the other side of this cutting plane. On the other side of this cutting plane is this entire part, including the vertical little bits. Okay, that is why I have to take that contribution also. If I don't take that, then a portion of the cross section you are not even considering for your calculation of the Q. That is going to be wrong.
Okay, sir. So basically, depending upon the cutting plane, we have to take the block or the complement of it in order to get the calculation done.
Yes. So in the previous problem also it was the same thing. Okay. In fact, in every problem, wherever there are nails present or some kind of adhesive present, you can also have some kind of glues present. Sorry, not glues, welding present. Okay. So for example, you can have this kind of a thing. Where is white? Okay. So maybe you have things like this. Okay, so the top part is welded to the bottom part through some weld here. So just like you have the case of two nails, two series of nails, here also you have two contributions from the welds. So you take that appropriately. Okay, similarly, if you have, instead of this, if you have adhesive present, some kind of favicol is there. Some kind of favicol is here present. So then also fine. Now this, I mean, favicol, there is no two series of favicol, there's one adhesive. So you take the cutting plane here. Okay, just like before, you take the cutting plane here, consider the part which is below it, which is above it, like that you do. Here also you do like that.
Okay, sir. Okay, sir.
So whatever the two surfaces are being joined, so you start your physical visualization of the problem from that. It'll be easier to think of it. So I hope it is okay. So we'll continue with the transformation of strain chapter with all the fundamental derivations and everything tomorrow. Okay. All right, guys. When do you have your dynamics class test?
Tomorrow, sir.
Tomorrow. Okay. What other class tests are left?
Sir, till now only dynamics and then mid-set.
Okay. All the best. Okay.
Sir, when is your office hours? Like in the evening?
I have no office hours. I am not an American professor.
So if we want to meet you in the office, when can we do that?
Please don't meet me in my office. Just catch me outside the office. And when you have sufficient number of doubts, you tell me. I will have this kind of an office hour where 4 or 5 people will turn up. Okay. This is better because this gets recorded also and others can see later on. Okay, I'm stopping the recording.